Guys, so in the last video, we talked about how ionization energy changes as we go across a period and down a group. And I told you today that we were going to talk about the exceptions. So these spots that we circled, where ionization energy should increase as I go across a period, but in these cases, it went down. All right. So let's look at two of those elements. So I have beryllium is Be, and I have boron. And beryllium has 4 protons, and boron has 5 protons. Right. Now the ionization energy is 900. And boron should be higher. It has more protons. We would think it would hold on to the electrons better and be harder to remove them. But if you look up the ionization energy for boron, it's only 800. So we need to talk about why that is. If I do electron configurations, beryllium is 1s2, 2s2. If I do boron, 1s2, 2s2, 2p1. Okay, so why would it be easier to take an electron off of boron? You see how this one electron is in a p orbital, and I have 2 s orbitals here, making more shielding. So as I jump from where the S block fills up to where the P block fills up, even though my number of protons is getting higher, I'm now starting to put electrons in the P orbitals that are a little bit further away from the nucleus, have more energy, and they're not going to be held on to as tightly, even though the number of protons increased. Okay, so jumping from that S block to that P block, there's always going to be like a little dip, and then your pattern will continue, that your ionization energy will increase. All right. The next example we're going to look at is N and O. Another exception. N has 7 protons. Oxygen has 8 protons. So you would think, okay, the more protons, the more tightly the electrons are going to be held onto, so it's going to be harder or take more energy to remove. Well, it takes this much energy to remove nitrogen's valence electron, and it only takes this much energy to remove oxygen's. So it doesn't make sense if we're only looking at atomic number. So here again, let's do electron configurations. 1s2, 2s2, 2p3, and for oxygen, 1s2, 2s2, 2p4. All right, so now we don't have the same issue that we had before, where we've created a new type of orbital. They all have 1s and 2s and 2p. So now we need to look at orbital diagrams to get a little more specific. If I draw out the p orbitals, right? And according to Hund's rule, I fill in those electrons. We know that they want to separate before they pair up. So those are what the valence electrons in nitrogen would look like. Where if I do the same thing for oxygen, I have 3 boxes. 1, 2, 3, 4. What do I have going on in this orbital? I have increased repulsion. So if those are electrons are already pushing away from each other, it's going to make one of them easier to remove. Okay, so that's when you compare column 15 to column 16. There's always going to be those paired electrons in that first orbital that'll make it easier to remove. So as far as like when we were talking about explaining things in terms of atomic structure, all right, this last this last thing down here, this electron-electron repulsions, that's really what you want to use to explain the exceptions to any of the trends that we talked about. The nuclear charge and the shielding was really what explained why the trends do occur, and the repulsions would explain these exceptions. Okay. All right. So, guys, being that we're talking about ionization energy, I want you guys to take a look at this chart. Now, this is something that you guys are going to have to be able to do that the Regents classes would not be asked to do. Now, when you look on the reference tables for ionization energy, it's the first ionization energy, which means the amount of energy it takes to remove the outermost electron, the first electron in the valence shell that's the furthest away from the nucleus. Okay. And that's always going to be the easiest one to remove because it's got the most energy. It's the furthest out there. Okay. So if I look at sodium, I'm going to use sodium as an example. This column is for sodium. 496 is its first ionization energy. So if I do the electron configuration for sodium, it's 281. That means if I want to remove that valence electron and turn sodium into 2-8, it's going to take 496 kilojoules of energy to do that. So that's how much energy it would take to turn sodium into sodium plus 1. Okay. Now notice, guys, if you go down the chart, they tell me how much energy it's going to take to remove another electron and another electron and another electron. Notice that the amount of energy is getting greater and greater and greater. As you remove electrons, now I'm not trying to remove an electron from the third shell. I'm trying to move an electron from the second shell. The second shell is closer to the nucleus. Those electrons are held onto more tightly by the nucleus. Therefore, they're going to be harder to remove. So if I want to turn 2-8 into 2-7, if I want to make a sodium plus 2 ion, it's going to take 4,562 kilojoules of energy to do that. Do you see that giant jump? A couple thousand kilojoules difference in energy because I went one shell closer to the nucleus, right? So wherever that big jump is, guys, that tells you how many valence electrons you have. For sodium, after my first number, the amount of energy changed drastically. So I know that sodium must have one valence electron, and now I'm pulling from inner shells. Magnesium, here's your jump. I'm going from 1400 to 7700. These first two electrons are the valence electrons. They're in the valence shell, so they're not so bad to pull off. This electron, the third electron that I'm trying to pull off, is from an inner shell. Aluminum has 3 valence electrons. How do I know that? Look at this crazy jump. 2,700 to 11,500 joules of energy. So these first 3 electrons were fairly easy to pull off because they must have been in the valence shell. Once I get to the 4th electron, now I am using a ton of energy compared to what I was using before. So you guys have to be able to look at ionization energies, and you have to be able to notice where the giant gap is. And that giant gap in energy tells you those first few electrons were valence electrons. Now you're attacking the inner shell. So that's something really important that you guys have to be able to do that Regents would not ask about. Talking about becoming ions, guys, we also need to know what happens to the radius of an atom when it becomes an ion. Okay, so let's talk about metals first. Metals, they become positive ions by losing electrons. Okay, so if I were to draw lithium, right? Lithium's got 3 protons, 4 neutrons. There's 2 electrons in the first shell and 1 electron in the second shell. We learned how to do this when we learned Bohr diagrams, right? Now, for lithium to become a lithium ion, what does it have to do? It has to lose 1 electron. So how is my picture going to look different? One whole shell is gone. So what happened to my radius as I turned into an ion? It got smaller. That's true for any metal because the metal always loses electrons, so the valence shell goes down. So the atomic radius, let's say the ionic radius is smaller. Okay, now nonmetals do the opposite. They become negative ions by gaining electrons. Okay, so if we do oxygen, 8 protons, 8 neutrons, 2 electrons in the first shell, 6 electrons in the second shell, right? Now, oxygen, when it becomes an ion, it specifically becomes a -2 ion. So how is my picture going to look different? 8 protons, 8 neutrons. If I'm becoming a -2 ion, I want to add 2 electrons, right? So my outer shell originally had 6 in it. If I add 2 electrons to that, what is it going to turn into? It's going to turn into 8. Now you would think, okay, well, I'm adding it to the second shell that's already there. My atom's going to stay the same size. Not true. 1, 2, 3, 4, 5, 6, 7, 8. Yes, the number of shells remains 2, but when you add electrons to your outer shell, the shells are going to spread out. Why? Because electrons repel one another. Negative particles do not like to be near each other. So if you're going to go ahead and add more negative particles, those electron shells are going to try to spread out. They're going to push apart. So for nonmetals, the ionic radius is bigger than the atom. Okay. Finally, guys, and this has to do with becoming atoms as well. When you see the words isoelectronic, iso meaning the same, electronic meaning electrons. So they're atoms and ions that have the same number of electrons. So let's talk about lithium and oxygen, which we talked about on this page here, right? Lithium's electron configuration is 2-1. When it becomes a lithium ion, how does its electron configuration change? Sorry, guys, that should be a +1, not a +2. If I'm losing 1 electron, my new configuration is just 2. What element on the periodic table has an electron configuration of 2? Helium. So the lithium ion is like helium. It's resembling the noble gas helium. Oxygen was 2,6. When I turned into an oxygen ion, what did my configuration change to? 2-8. If you look on the Regents periodic table, that's like neon. So when atoms turn into ions, their number of electrons change, and now you can have things that have the same number of electrons because the number of electrons is allowed to change. Here's kind of like wrapping it all up, guys. So if we think about ordering these from smallest to biggest, right? So these are all These are all 10 electrons. If you go through and you look at their atomic number and you either add for negative ions or subtract for positive ions, you'll figure it out that all of these have 10 electrons, right? That means that they all have 2 shells, because we know that 2 electrons can fit in the first shell and 8 electrons can fit in the second shell. So they all have a 2-8 electron configuration. So again, now I want to think about which one's going to be the biggest, right? Smallest to biggest. So what is in charge of how close those electrons are pulled in? The nucleus. So if I look at atomic number, these are listed in order, so that's nice. Which of these atoms or ions is going to be pulling on its shells the tightest? The aluminum is, because it's got more protons. So aluminum ion shells are going to be closer to the nucleus than anything else. So as we go this way, nitrogen is going to be the biggest. It's got the least amount of protons pulling them in, and my aluminum is going to be the smallest. So you guys have to be able to say what has the same amount of electrons as something else, and then what happens to the size, whether it loses or gains. Okay, and that is it on the periodic table. Give you some questions. We'll talk about it tomorrow.